Thank you. Okay, so the reason for choosing that title was that I thought I was the only guy talking about deep neural networks, but there has already been one talk. Nevertheless, it's still different because I'm not going to focus on the landscape. I will focus on the algorithms, which has a completely different flavor. So, okay, so that's basically capital P is my deep neural network. It's a composition of several maps. So the phi sub I denotes one input output map corresponding to the ith network. Okay, that's the typo already. It should have been beta 1. This beta is a parameter. So your concatenation of capital N maps parameterized by the corresponding betas, beta 1, beta 2, dot, dot, to beta N. And there's a kind of the entire concatenation represents one deep neural network, which takes some input and spits out an output, a noisy output. Okay, so these are some caveats. So there are two problems. So currently in the middle of the talk, I'll change here. And I am sticking only to giving the broad outline and not very detailed. But most of the time I'll just be talking. So in particular, the talk may be very short unless you ask questions. And the objective here, this is important, that this a large part of machine learning community is kind of, they just run a lot of simulations and some theories and report what they observe. And sometimes they come up with some observations which are kind of considered as curious phenomena which are not explained, particularly in the training process of the deep neural network. And I'm trying to explain them to the extent possible. Some are sort of easy to explain, some are not. So consider a feed-forward network which I just defined. And beta is this vector of individual betas. It's a big parameter vector. And suppose there's some optimal beta star which you are trying to learn. So I'll assume that at least for this talk, in general, for my theory, I need to assume that it's continuously differentiable in beta, which is not always true. So for example, one of the classical functions is what's called sigmoid, which is continuously differentiable, but more common, more popular, what's called rectified linear unit, which is not. And this has advantages that wherever it is differentiable, the derivative is only 1 or 0, that simplifies the overall network. So that connection is either there or not. Okay, so the input-output pairs are, the idea is that I keep feeding IID xn, and the output will be yn, which is the piece of beta star, which is the beta star is the true parameter of xn plus some IID zero mean noise with finite variance. Then, I mean, this is kind of a standard thing to do. So I define a loss function, which is expected value of some instantaneous loss, which I call f beta xn and yn, a function of beta xn and yn, which is, I have taken the most commonly used loss function, which is the square error. And I'll assume that f is also continuously differentiable, and it has some, I'll denote with respect to beta, and then denote by grad sub beta the gradient with respect to beta, which I assume to be Lipschitz, also with bounded second moment. These actually, some of these assumptions, because I'm not going into detail, they are not going to show up at all, but nevertheless good to have them. And in this slide I've got, okay. So f beta is the instantaneous square error, and define this map beta to h beta, which is the expected value of that expected mean square error. I think I called it L beta earlier. Now the algorithm is the kind of the rock star of machine learning, stochastic gradient descent. So this is a basic vanilla stochastic gradient descent. So beta n plus 1 is beta n minus a times the gradient with respect to beta of the instantaneous loss, which I write as basically what I am doing here is adding and subtracting one step conditional expectation. So Mn is the original gradient minus conditional expectation given beta n. And then I can write it as this function grad beta of h beta n plus Mn plus 1, where Mn plus 1 by construction is a martingale difference. Okay, so far okay. So this now fits the standard paradigm for stochastic approximation. Generally, one looks at algorithms which are xn plus 1 is xn minus a times function of xn plus martingale difference noise. So here the function happens to be minus k. So I'm going to digress a bit to advertise one result which I am not going to use for any specific purpose, but it motivates my formulation. And I also think it's a nice result which should be better known due to Austin response. So let X D be a compact metric space and mu is a probability measure on its Fourier sigma algebra. The support is connected, locally connected, etc. And for some large n greater than or equal to 2, you take the product space, n is cross x n times, and define the metric on the product as the maximum of the individual metric. That's one component. The second component is this function omega from positive real line to its closure. The continuous non-decreasing function will basically serve as a modulus of continuity. And the third component is I define gamma S as a projection from L2 mu to the subspace corresponding to coordinates spanned by the indices which belong to S. So S over the index set is 1 dot capital N. I take some finite subset of it. And basically, if I define some function f on this whole x raised to n and take conditional expectation with respect to the components corresponding to s, that's what I mean. Okay, so this is the theorem. Then for every epsilon positive, there exists an integer p greater than or equal to 1, depending only on x, epsilon, and omega, with the following property. The important thing is that these two for all n greater than 1. If f x to the n to x raised to n to r has modulus of continuity at most omega for that metric dn, then there exists a set S which contained in the index set 1 to n with cardinality less than or equal to p, so that the L1 norm of f minus the L2 projection to the space corresponding to S is smaller than epsilon. So this is in words, and this is the fact I need because I'm going to do something else, but use this as a motivation. A hard constraint on the modulus of continuity forces function to depend only on a subset of variables. The reason it's important is that in this part of the machine learning folklore of, if you consider large overparameterized neural networks, the input-output map depends largely on a proper subset. So this is what I want. Huh? No, PCA, okay. I mean, the PCA is possible. I mean, it has to depend, only few parameters have to be prominent, the rest are not, because of the constraint. Okay, yeah.
Previous page, the result, the previous one. So X super n is your parameter space, is that correct?
Yeah, I mean, it's not thinking of a parameters and product n times product of some space X with itself. Now I'll apply it to neural network parameters, but right now it's just damage. Yeah, so I'm going to use this just motivates this model. So my parameter is beta. I assume I can partition it at alpha, comma, gamma. And the function h beta is the form psi of alpha, comma, epsilon y, or epsilon gamma. Okay. So I want to capture the fact that it depends mostly on the part alpha and less so on path gamma. So this is, I said, it's a stylized model. Stylized because it's not, you need not have clear-cut separation of scales. There could be continuum of scales or multiple scales, etc. But I'm assuming we have two kind of dominant scales which are we can identify. Then if I write down the gradient descent, I get that. So this becomes what's known as 2 times scale stochastic gradient descent, because the alpha n has a step size is A, gamma n has a step size epsilon time A, which is much lower. So the descent will be much lower in the gamma variable. So this is actually been around in stochastic approximation literature, but there are 2 key differences. Okay, there's one key difference.
Shouldn't that be epsilon gamma n in the psi?
Oh yeah, should have been epsilon. I might, this error may repeat. And the way to, I will come to the how one normally analyzes is, you consider basically like it's a 2 time scale system. So you sort of analyze the fast time scale pretending the slow time scale is frozen and look at where it converges. Suppose it converges to some point, which depends on the frozen value of the second variable. Then plug that into the second equation and analyze that separately. I will come to that. But what I'm going to do here, generally you think of the fast regime and slow regime. Here I'm going to talk about 3 regimes. The third one is the important one for this particular talk. So that's why I have numbered these as 1 and 3. That's the classical scenario. The middle one, which is hard to analyze and but more interesting here. So if I treat gamma n as a constant, that's a slowly moving thing, so it's quasi-static. So alpha n approximately converges to, for fixed gamma n, it will converge. Okay, I'm assuming these are gradient descent, so I'm assuming it as this is just for giving the intuition. So I'm assuming unique minima and all that. So gamma n will converge to some, alpha n will converge approximately to this lambda of gamma n, because gamma n is quasi-static. Actually, what one can prove, the precise statement is alpha n minus lambda gamma n goes to 0 almost sure. So it tracks lambda with the minimum of the over gamma. The slow time scale, so because of that, you can, in the gamma dynamics, you can replace x by lambda gamma n. And then this is kind of autonomous. I mean, the dynamics involves only gamma n. There may be x dependence here, but it doesn't matter. The noise is getting read out in stochastic approximation. So this will converge to the minimum of psi of lambda gamma comma gamma, and that's a classical 2 times scale. And this is, I mean, I'm again simplifying. If the things are not nice, it could be a subgradient descent also by. But this itself is justified by Danskin's theorem. It says that basically gradient, and the vanilla version is the gradient of min over y of fxy is gradient of gradient over x. Okay, I will learn about it. This actually is correct under nice conditions. Otherwise, one gets subgradient, but some version of this is always true by a theorem known as Danskin's. Quite popular in optimization, also in game theory. So this medium regime is when these are comparable. They can be comparable because see, you have come to a point where for this gamma, the gradient in the first variable has decreased to a certain level, so it's small. The gradient of the second, with respect to second variable may not be small, but you are multiplied it by epsilon. So before that takes over, there can be a patch where they are comparable. And help breaks loose. There's a multiple phenomena with exotic names, which I did not cook up. It's from machine learning literature. So I will describe them later. And first, I'll give some intuition. The thing is that because the y is being multiplied by epsilon, what you get is what's known as pinched landscape. So you are going down something like this kind of a landscape. So what I have on the next slide is the kind of top-down view of it. It will look like this. So this dot 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 is the y trajectory that it's kind of sloping down, it's going down nicely, but the x with the comparable steps, say just go bang like that. It will slowly go down because it's kind of decreasing. Eventually, it will kind of look, it will start going that and go down and down, and x will also become small. That's when the third regime takes over. But while the second regime is on, it's contributing a deterministic jitter. And its contribution to variance will grow as order of n rather than square root n, which I didn't show here. So that causes problems in the middle regime. And so I mentioned this key phenomena, something called double descent, which has, okay, there are a couple of things I should mention here. One is that this number of iterations, I think later on I call it epochs. So one thing specific to double descent is originally this axis was number of features. That's how it was originally analyzed by Belkin et al. But subsequently, people worked on time axis. So in machine learning, mostly it's epochs. It's basically, you run, it's not just clock going 1, 2, 3. You run one experiment, then you run another, and so on. So you just count those. So those are called epochs. So this, and another comment about this and the subsequent figures is that they are too nice to be true. I mean, the actual figures will be very jagged, experimental figures. And secondly, the effects are highly exaggerated here so that they become clearer. So you get this initial descent, then there's a middle region which actually ascends and then it descends again. So I should also mention another thing about this. Yeah, one thing is that this is usually, this is always there, rather, logarithmic scale, and this descent is actually much slower, which is understandable because it's a slow time scale. Another important thing is that different scenarios attach different importance to this. So in Belkin's, one of this, Belkin's work which measured, had a major impact. What we observed is that, see, typically, it's more, okay, actually the next one is a more correct thing, but okay, I will go to that. The same thing, but it's kind of flat. So typically you go for the, you stop till the gradient kind of becomes small. So tradition was to stop here and then compared to the exact things which sort of you just, okay, this is the ideal picture, but you stop here and miss out on a lot. What Belkin found that you wait long enough, it descends again and you get a much better solution. But there are also other situations where you want to stop because the situation is such that you have captured what you want. If you wait long enough, you'll go down, but then you are you are modeling the noise as well. So there are these two, both the possibilities exist. So this is called grokking. Apparently, a word comes from Martian lingo in some science fiction novel by Robert Heinlein. Don't know what it means to the Martians, but to me, it has. There's another thing called catapult, which is basically a repeated thing, similar thing, more than 2 times. So this is the kind of thing which I can explain this way. Now, again, there's another thing. It was not obvious that this decomposition was unique. Maybe there are, depending on which seed you start with and what noise you have, you will end up with a different choice. So the answer, so this is what sort of emphasize it's the simplest one in terms of having a smaller number of dominant variables in an appropriate space. And this I can say about both the time scales. So I'll just stick to one time scale for simplicity. And this result is based on large deviations for small noise limits applied to constant step size stochastic gradient descent. And this is this nice paper, Azizian, Yutler, Malik, and Motikopoulos. And they show that a large deviation principle holds for small noise limit of the stationary distribution. So I'm always looking at the stationary distribution. And with a parameter A, so the step size is A. So it will be it is similar to Friendly individual potential, but it's not the same, which is the important part. This paper actually emphasizes that. So my algorithm is say beta n plus 1 minus A times dot. So the stationary distribution will be something like e to the minus e by A. So this I want to contrast with xn plus 1, or maybe let me write the exact minus z. This is Langevin dynamics. Then you would get proportional to, so approximately proportional to, so get e to the minus f by epsilon. But the thing is that here is square root epsilon, and it's not the you this is grad f, you get f here. That's not the case here. It's a gradient descent, but the potential is v won't be same as f. And that, so one hopes that if A is small enough, it should be close to it. That point I will come to later, but that's the important thing to note, that the Friedel potential, I'll always refer to these objects as Friedel potential, regardless of whether I'm referring to Friedel work or not. All it means is that it's a potential associated with small noise limit, for the large deviations associated with the small noise limit of stationary distribution. Okay, so this is what I just said. The stationary distribution starts looking like this for the stochastic algorithm. Now, given that something looks like this is a ready result, which I'm going to use now. So if V is twice continuously differentiable and the Hessian is non-singular at each global minimum, so the global minimum are not flat, then the asymptotic probability mass at each global minimum is given by this determinant of the Hessian raised to minus half. Is basically product of its eigenvalue raised to minus half. Okay, so this is a known result from Wang. So what it suggests is that only few eigen directions matter. So you look at the corresponding eigenbasis for that at that point. Then you cannot have too many large. The weight will be more at the global minima, which has fewer large lambdas, large eigenvalues, which means that it will prefer kind of flatter minima that afford a compact description in the corresponding eigenvalues. So this is the first part. The second part is just one problem for future. So the thing is that, as I said, if A is small, hope that Athreya et al. Potential is close to Friedel because you are running a gradient descent. You hope that the global minima of something you get are close to the global minimum of the original function. So that kind of thing is missing. One possible approach we are hoping to pursue is so therefore the potentials have a control theoretic interpretation, which was actually due to Friedel themselves they're in the book, but they assume compact state space and there are successive extensions thereof. But you can do that for both these cases and then try to show that the control theoretic interpretation as a value function means that the optimum cost to go from point X as a function of X in this context. Okay. If you can show that for the two scenarios, it remains close as long as A is small, then that kind of relief in a sense that HJD is not too far off from the actual minimum. So I'm going to talk about this a shorter piece. So then talk about generative models. So I'll take the most naive possible picture of a generative model. So start with some probability measure on a Polish space, say mu naught, and at time n I generate mu n plus 1 from mu n. taking mu n as a seed, I generate another. So these are random probability measures. So given a random probability measure mu n time n, I generate mu n plus 1 with this property, that mu n is a conditional barycenter of mu n plus 1 in the following state. That you take any a, expected value of mu n plus 1 of a given the past is mu n a. Okay. So in particular, it implies the tightness or apparently relative compactness of this thing. So technicalities are not hard here. So most common example, the original generative model was actually empirical distribution. You start with some distribution, you generate a lot of samples according to it, take the empirical distribution of that, generate a lot of samples according to that empirical distribution, and keep repeating. Okay. And there are also this one Bayesian update scheme for parametric Gaussian models, which is one of my friends in IIT Madras working on. That also has this property. Okay, so you can see that for bounded continuous f, just by the construction integral f d mu n is a bounded martingale, so it will converge almost surely. You can take f from a countable convergence determining class, which always exists, and therefore mu n itself converges almost surely. And we have a Markov chain which converges almost surely. So it has to go to an absorbing state. That means mu n is going to some direct at some random measure gamma. So this is sort of mathematical interpretation of collapse. What happens in generative models that after a while you start getting the same thing. You just throws up the same image or same whatever, or close to it. So this I have called pure because there's to idealize the model, but still reasonably close to, I mean, it at least motivates what you see. So the reason I started with the police space is not for sake of generality. Actually, you need it for at least a Banach space. So this is considered what's called a diffusion model. This is a generative model for product of continuous functions from C0t to R2 usually, because it's an image. Now, see, this thing is I'm going to give a very vanilla description of how it started. So, but now it has been evolved so much that this description is no longer valid, but nevertheless, even the original thing itself did a lot of miracles, and you must have seen at some stage a lot of fake, I mean, photographs of people who don't exist or even videos, etc. They are generated this way. I mean, yeah, it seems very naive, but it does what it aims to do. To start with some image and take it as an input to an Einstein union, which process go for long into the future, so that some very large t. So this is almost Gaussian noise. You take that as an input and run the reverse diffusion, and you will get something else. You consider that as another sample from the same distribution from which this came. So that's the idea. So yes, this is a way of this kind of, again, a generative model. You generate more and more samples from the same distribution, and there's some problems like that where it's a little different problem, but I'll come to the details later. But basically, it promises to fall into that trap, except that it's not just that, there's more to it. So the thing is that once you write down the backward partial differential equation, so this is the forward Kolmogorov equation. I mean, backward is not backward Kolmogorov equation. Backward, okay, so this is forward Kolmogorov. Backward equation just means, suppose this was, say, phi t, just phi t minus t, reverse time. It's not the backward Kolmogorov. The same equation with reverse time. If you do that, you get some unpleasant term here. This term pops up where p. This is the density of xt at time t. You get grad log term coming in the drift. Okay, this goes back to the earliest is in fact one control engineer called Brian Anderson from Newcastle, and later on there were further work by Hazra and Hausmann, and also Hollander, probably others. But it's kind of been around in probability and control for a while. So this thing you don't know. And it's called a score function. That's a terminology created by the machine learning people. And one problem is to learn it and iteratively learn it. Start with some guess, and so it's not a standalone generative model, there's also some tuning of the parameters going on concurrently. And the phenomenon they observe, again, it has a different name. They call it memorization. You keep seeing the same image or some near clone of it for a while before something else happens. Some long patches of repetition. So this, I feel one can view as a paradox collapse, because essentially, I mean, if you are not updating anything and you had exact backward gradient, you keep doing the same thing again and again, it would be an exact generative model just on a monarch space instead of image. Okay. But because you are tuning it, and there are other issues also, that there's too much of an idealization. There are approximation errors and noise from consciousness. I mean, this is a whole industry actually enormous. This is incredibly naive. The things have moved a long way from this extremely sophisticated techniques. This is actually, I don't know, those who were here for the previous event I attended, there's a person called Dheeraj Nagaraj in Google Research, Bengaluru, who is an expert on this, and he did give a talk on that. So, but here all I want to say is that this is fairly far from idealization. So you think of it as a part of collapse. Yeah, so that's it basically. And that kind of my explanation of memorization as sort of punctuated collapse or part of collapse. So that's basically the end of talk. And I want to acknowledge for the people who funded this, so Google Research some time back, and now the Government of India. And the last part is work in progress jointly with Siva, Athreya, and Bhattacharya from Ministry of Science. Currently, there's a manuscript sitting for approval by Lord Siva. Once that is done, we will put it on archive. Okay. And while Googling for something or the other, I noticed a blog by this guy who is a data science guru from Kent. I found it interesting. I used to write, "Thank you for your attention," and now I don't.
Thanks. Thank you for the talk. Now I think it's time for questions.
I have a basic one. In the diffusion model, is there an easy example to understand the backward process, like where it works quite well? Like you get good samples of the data set again. So you run the
okay. So yeah, one of the things they are doing is kind of current frontier is that there are some steps whereby you can push the trouble to the initial condition, and you kind of condition on the initial condition, do some transformation, so you end up looking at a Gaussian process initially, where things become easier. But it's conditioned on initial condition. If you put that conditioning back in, that advantage goes off. But they're building algorithms around this. So there's some dependence on initial condition, which you treat parametrically. Then the rest of the dynamics is nice, including the gradient and so on. But there's some initial condition hanging around as a parameter. Then you try to reach that.
Like if you look at like the chemistry Nobel Prize, for example, the protein folding, they did exactly similar models, right? So, but are there some simpler models one can try and code them ourselves to see any good references for them?
I think the extent I understand, see, my source is Bhattacharya. This conditionally Gaussian trick is the current. So this person called, I mean, he is kind of one of the pioneers here, Stefano. So he has a small book which probably will appear, the Now series or somewhere, I don't know. But right now it's available online. So he gives a nice exposition of the.
Because whenever I've tried to noise and denoise, I only get noise again. So whenever I try to noise and denoise, I only get noise again. I don't get data sets.
So just have a look at this, maybe you see.
I have two questions. So the first question is like, why should you expect this repeated collapse? Like in the reverse diffusion process, you mentioned that there are several iterations. You see the collapse, but then after a lot of iterations are done, then you would see a new image.
So the thing is that it's not a pure generative model because you are tweaking a parameter and it's being tweaked on a slower time scale. I don't have any precise statement for this, but because it is a slower time scale, I think it will sort of tend towards collapse, but by that time this parameter would have moved elsewhere.
So another is there another intuitive explanation for like why do you see a double descent in the first few slides for error rate versus number of epochs? Why there's a double descent, like an initial regime where your error is decreasing, and then it's increasing again? So why there is an increase?
No, this is as I said, my figures are exaggerated, but it is observed, and I think one of my figures. This one. No, not this. Yeah. What happens is that in this regime, this deterministic jitter contributes a lot of noise at the order of n. This deterministic noise, more or less.
Are there other questions?
Is it working? Yes. Okay, so I might have a naive question because you were comparing the Langevin dynamics with this gradient, stochastic gradient descent, but I think I missed a bit because there are two rate functions which are different. And is it because you expect like the noise to be multiplied by, I mean, here it's just additive noise, right?
Yeah, so here, okay, so this part is known because basically this is a correct rate function, but in this equation, the main difference is that here the noise is on the same scale, A times that. So they show existence of a large deviations principle, but they themselves say that it's not same as F.
Okay, they don't have an explicit.
Yes, so time scale is different. It's A times n plus 1. Here it would have been square root A.
Yes.
If it discretize it at Langevin algorithm, it will be square root.
Okay, thank you very much. Yeah.
So, sorry, this is about your last slide. Yeah, so if you didn't, in the last one, just the acknowledgements part.
Oh.
Even the next.
Oh.
So if you didn't deserve the attention, but we still gave it to you, then we deserve the thank you.
Sorry, I didn't get that.
Then he wants he
So I was saying that if you didn't deserve the attention, but we gave it to you, then we deserve the thank you.
Yeah, I think.
Okay, thanks.
I think this is probably a beautiful conclusion. So let's thank Vivek again.